Is this you this morning? Well, let's get up and let's do some chemistry. Good morning and welcome back. I'm going to get right into it and get to our calendar for today. Today's the 13th, and it could be the 14th for you. Two big things: respond positively to everyone you interact with, and or play a game that you enjoyed when you were younger. Make sure you do that. Hey, let's get right to today's lessons. I'm going to go over this. Main purpose of this video is to show you three problems. Two of them are review, one is new. So I'm going to be showing you a combined gas law, which is the one I've been showing you, just a little bit different than other ones. Most times combined gas law is with pressure and volume and temperature. I added moles to it, which works fine, and I'll be showing you a problem how that works today. I'm going to show you one that's a little bit more involved because it has more than just two different variables, and then I'm going to do a problem with the ideal gas law, and then I'm going to ask you to solve a few. So here we go. So this first problem is from the Unit 7 problem set, number 8. Letter D, and you'll notice that I have the combined gas law already written out, and then I'm just showing you a little different way that you could solve these things. In the past, I went and I determined which of the numbers were pressure, volume, temperature, moles. I'm still going to do that, but now I've listed out the pressure, volume, temperature, and moles, and I'll fill them in that way, and that will help me figure out what to do with my equation. So I'm going to underline all the major players that we have. We have moles of nitrogen and 400 millimeters of mercury. That's a pressure value. And then we have another moles. So the two big things we have are moles and pressure. So filling those in, it looks like when we add some more molecules, I want to know what that's going to do to the pressure. And since volume and temperature are not involved there, we're going to assume that they remain constant, so we don't need to worry about those. So looking at our equation, we're simply going to cross off the things we're not going to use. So that's volume and temperature. And what we're left with is our equation. So P1 over N1 is equal to P2 over N2. And since it's something over something else, that's going to be a direct relationship. So if the number of moles increases, then we would assume that the pressure increases. So we're just going to fill it in and then solve for that. So 400 times 2.5 divided by 0.5 is going to be equal to a pressure of 2,000 millimeters of mercury. That literally means that's in a column of mercury. Mercury's going up 2,000 millimeters, which is about 2 meters. So why don't you pause this and take a look at problems F through J, I believe it is, in number 8. Those all have the answers to them. Solve as many as you need. I'll be available on Zoom. You can do a Zoom chat with me and request that if you need. And I'll see you in just a little bit with the next problem. So the next set of problems from number 9 in your Unit 7 problem set, really the same type of problem, but what's a little bit different, as you see in the instructions, it says it can involve 2 or 3 or even up to all 4 of the variables that we're looking at. So I've included or have listed out each of the variables, and I'm going to do what I did last time, is I'm going to fill those in and see what I have to work with, and then just plug them into my equation. And whatever I don't have, I'm going to eliminate that and assume that is constant. So I'm just going to go over problem A with you, and then there's 4 other problems that you can work at your leisure. You have the answers, you can see how well you do with those. So our starting values are 40 liters of a gas that's under 1 atmosphere pressure, and it's at a temperature of 200 kelvins. And they're increasing the pressure by 6 times, and they're increasing the temperature by a factor of 3, up to 600. So they're making those gas particles go a lot faster, and they're going to be hitting the sides of the wall a lot more because of that. So they want to know, if you don't change the number of particles, that's moles, N, what has to happen, or what's going to happen to the volume. So we're assuming that the container is something that can expand or contract. So I'm going to fill this in with our combined gas law. So P1 V1 over T1 is equal to P2 V2 over T2. So a little bit more complicated. We have to be able to isolate V2 by itself. So to get the question mark by itself, we're going to multiply both sides by 600. And we're going to divide both sides by 6. And then we're going to solve. So it'll be 600 times 1 times 40 divided by 200 times 6. Or you could do that whole top and divide it by 200 and take that answer and divide it by 6. Ultimately, it should work out to be 20 liters. So the volume in this particular case has actually gotten smaller, and that's the reason that the pressure has also increased. There are 4 other problems, so solve at your leisure, but make sure you go through those and see that you can set those up. We've been fortunate so far that temperature has been in kelvins. Be aware of that. If the temperature is in Celsius, you'll need to convert it into kelvins. So the last problem involves the ideal gas law. And you'll notice, I hope, that the equation is almost exactly the same as combined gas law. If you rewrite this, where R is equal to PV over NT, PV over NT is what we used for our combined gas law. R is the ideal gas constant, and that was mentioned in Professor Dave's video. And that's one of the tricky parts, is you have to be aware of which R value, which ideal gas constant to use. And again, that's based upon the pressure. So I'm going to work out problem number 10A with you. And doesn't say this, but we're going to do this pressure in atmospheres, since I already have an answer for that, and show you how to go about solving those types of problems. And then I'd ask you to go ahead and do problem at least 10B, but maybe also C. Be aware of those ones. They are in degrees Celsius. So let's go ahead and work out 10A. What you should notice about these types of problems is that there is not a change in any of the values. They simply give you one value of each of the different variables, and then you're supposed to solve for whatever's left over. So I call it a right here, right now sort of situation. It's not here's the beginning situation and here's the end. That's where you use combined gas law. It's what's the conditions right here. So let's go ahead and fill in our known values over on the side, and I've listed that out. And in the problem, it doesn't tell you what the pressure is going to be. Like I said, we're going to do an atmosphere, so we're going to have to use an R value that reflects atmospheres. So I brought over the 2 R values that we're going to be using mostly. Those are actually from the front of the homework packet, towards the bottom. And what I've done is I highlighted the value and what pressure they're in. So the blue one is in atmospheres, so that's the one we're going to use. If it happens to be in kilopascals, then you're going to use that other value and substitute in that value for R. So that's going to be our next step, is we're going to write out the equation, substitute in, and then solve, in this case, solve for P.